Canadian passenger and freight rail traffic has increased significantly in the past 2 decades, placing increased stress on our rail network. This has been exacerbated by growth in the transport of dangerous goods. For these reasons, there's greater impetus than ever to mitigate the risk of rail accidents. In 2019, there were 1,246 major railway accidents in Canada, a 17% increase from the previous 10-year average. Many of these were caused by track surface defects and abnormalities in rail track geometry. Such accidents may lead to major derailments, which may involve explosions, environmentally damaging spills, major economic costs, and even human fatalities. The goal of our team's iGen 430 project is to create a modular device that harnesses machine vision to be used by Canadian rail companies and is capable of accurately detecting and reporting track defects to prevent such accidents. Our design was constrained by the geometry and regulations of existing railways, in addition to our project budget and timeline. After a process of iterative design, we developed a modular device that integrates mechanical, hardware, and software components. We designed our device to attach to existing rail cars and run fully autonomously. Compared to current rail inspection methods, this will reduce labor costs and the possibility of human error. We designed a robust steel frame as shown here, which is capable of securely clamping to a rail cart and houses all of the necessary electronics. We created a lightweight aluminum arm on the structure to mount the camera we will use to photograph the rail. The arm is extendable and has hinges which allow the camera to be placed directly above the rail for many different rail car geometries. Our design includes a weather-resistant GoPro Hero 7 camera, which is used to capture videos of the rail at a high frame rate. To ensure consistent image quality and defect visibility under all anticipated lighting conditions, we also included a GoPro light module equipped with a diffuser. The device includes a GPS, which is used for location sensing. With a GPS, we can keep track of the locations of rail defects. The electrical components are all controlled by a Raspberry Pi 4 microcomputer. To satisfy the device's power requirements during operation, it will harness electrical power available near engine cars. Once the camera has collected videos of the rails, the videos must be processed to identify and characterize defects. Our processing pipeline involves image extraction from the videos, image segmentation, filtering, canny edge detection, huff transform, line grouping, and defect geometry calculations. Since we couldn't run tests on a real train, to simulate the real operation of our device on the railway, we used a motorized cart that we built last year. The arm of our device, equipped with the GoPro, was mounted to the base of the cart. We collected videos of the rail using our selected camera settings and collected GPS data while the cart traveled at 8 kilometers an hour down a section of unused rail. Shown here is a video taken with the GoPro during one of these tests. We can see that while the cart certainly experienced some small vibrations, the video is very stable. Qualitatively, we can clearly identify a major vertical crack in the rail. Next, we ran this video through our image processing algorithm to see if it accurately detects the vertical crack. First, the algorithm extracts frames from the inputted video. Next, it removes radial distortion introduced by the GoPro's wide-angle lens. Then, the railhead is extracted from the image to exclude surroundings from subsequent analysis steps. To detect features in the image, canny edge detection followed by the huff transform is done. Here's the result after the huff transform was performed on an image containing the large vertical crack. Here's a zoomed-in view of the same result. The next step here is to group nearby lines together into single defects, as shown here. Lastly, we collected the geometrical features of each defect, such as the defect area and aspect ratio. These geometrical characteristics were used to assess defect severity. Once the processing script has processed the entire video, the results are all printed and summarized in a single, easy-to-use Excel file. The Excel file includes data for each frame, including GPS coordinates, defect type, if any, and the defect danger level. The user can easily filter the results to find specific defects. If we filter for cracks, we find that there were 2 frames in which a crack was found by the algorithm. The user can click on a path to images for each frame and verify the presence of the defect. As we can see here, the algorithm did correctly detect the large vertical crack that we identified earlier by eye. Overall, this provides the user with all the tools required to determine if a defect should be monitored or repaired manually. We envision our device being deployed on hundreds of trains throughout the country to perform more frequent, low-cost, and robust rail inspections than currently available. If implemented, this system could enhance the safety of Canadian rail networks by lowering the risk of derailments which harm people and the environment.